Hello, this is Professor Matt Katroulis of Rio Hondo College, continuing with my series of lectures for Chemistry 110, and this lecture is on Chapter 11, which continues our study of organic chemistry with unsaturated hydrocarbons. You'll recall that in the last video lecture we talked about alkanes, which are saturated hydrocarbons. Unsaturated hydrocarbons, on the other hand, contain at least one double bond or one triple bond within their structures. The reason we say that these molecules are unsaturated is because when they are allowed to react with hydrogen under conditions usually involving a catalyst, which we'll study very shortly, they will add hydrogen to their structures. On the other hand, if you try to add hydrogen to an alkane, like say pentane or hexane or octane, the hydrogen will not add. In effect, the carbons in saturated hydrocarbons have as much hydrogen in their structure as they can possibly hold. We divide the unsaturated hydrocarbons into three different functional groups. So the first functional group are the alkenes, and the alkenes contain the carbon-carbon double bond. An alkyne contains a carbon-carbon triple bond. And then aromatic compounds, which contain benzene ring in their structure, and this is the symbol for benzene. This should all be a review from the last chapter. Here are representative examples of all three types of molecules. Here we have ethene, which is an alkene, owing to its carbon-carbon double bond. Ethyne, also called acetylene, and used in blowtorches. And ethyne is an alkyne with a carbon-carbon triple bond. And then this compound here called orthoxylene, which is aromatic because it possesses a benzene ring in its structure. Now recall that for alkanes, all of the carbons that we talked about had a tetrahedral shape. All of the carbons made four bonds to four different atoms. In alkenes, though, the structure is going to be a little bit different, and the same is going to be true for aromatic compounds. All of those carbons have a trigonal planar shape, and there are 120-degree bond angles associated with them. Alkynes, even though the carbon makes four bonds, three bonds are to one atom and one bond is to another atom, that gives us a linear shape. And so, as we saw earlier in the class, linear molecules have 180-degree bond angles about the central atom. Just like with alkanes, these compounds are almost entirely nonpolar. And that is assuming that we don't have any other functional groups in the molecule. If there are other functional groups, that makes the situation much more complicated. So what do we say about nonpolar molecules? Well, nonpolar molecules don't tend to dissolve very well in water, for one. They tend to be much more soluble in other nonpolar solvents. They also tend to have fairly low melting and boiling points relative to other functional groups which have heteroatoms. There are going to be some exceptions to that, but this is a general rule that we should usually follow. So now we're going to change the rules for naming that we learned with alkanes and cycloalkenes slightly to accommodate alkenes and alkynes. Now the modifications that I'm going to make here are very important and will apply to other molecules that we talk about in chapter 12 and 13 on some level. So when we start introducing new functional groups, it's not like we have to completely rewrite the rules and start all over for each type. There's just going to be small changes for each one of these functional groups. So recall that for alkanes we said the parent hydrocarbon is the longest carbon chain in the molecule. For alkenes and alkynes we slightly change that. It is the longest chain that contains the triple bond or the double bond. In other words, both carbons in the double bond or both carbons in the triple bond have to be part of the parent hydrocarbon. We number in the direction that gets you to the double bond or the triple bond in the lowest number possible. That's going to be the case for all of the remaining molecules. You're going to number in the direction that gets you to the functional group first. Recall with alkanes, we didn't have functional groups. We didn't say that alkanes had a functional group. The rule for alkanes was you number in the direction that gets you to the substituent with the lowest possible number. So first priority goes to the functional group. So you want to get to the double bond or the triple bond with the lowest possible number, and you must number through that bond. So for example, if the first carbon in the double bond is carbon number 2, the next carbon in the double bond has to be carbon number 3. When we name the compound, we have to specify the position of the double or the triple bond, and we state that before the name of the parent hydrocarbon. So for example, if we have hexane, and let's say instead that we have a double bond between carbon 2 and 3, that's going to give us, as you'll see in a moment, hexene. The name of that will be 2-hexene. So, as I just mentioned, for an alkene, we change the ending of the parent hydrocarbon from ane to ene. And you could probably figure out what we do for an alkyne. For an alkyne, we change the ending from ane to ine. This is going to be an important type of modification that we're going to make for all of the functional groups. For example, when we get to alcohols, the ane ending will change to -ol. When we get to ketones, the ane ending will change to -one. So each of the functional groups will have their own particular ending. So let's practice these rules. Let's start off here with a simple alkane, which we learned how to name in the last chapter. So this is a straight chain alkane with 4 carbons. This is just butane. Good. What about this molecule here? Well, it has 4 carbons, so its parent is going to be butane. The numbering is through those 4 carbons. We're going to number it in such a way that we begin the alkene as low a number as possible. So in other words, I want to number this so that the alkene starts on number 1. If I numbered the other way, 1, 2, it would begin on carbon number 3. So we want to number this way. So the name of this is going to be, well, first we have to specify where the double bond begins. It begins on carbon number 1. And then we're going to need to change the ending from ane to ene for alkenes. So this is 1-butene. Remember that we need to use a hyphen to separate numbers and letters. How about this compound over here? If we go ahead and take a look at this one, we'll see that we also have a 4-carbon chain. It also has an alkene, and regardless of which way we number it, 1, 2, 3, the alkene begins on carbon number 2. If we numbered it this way, 1, 2, it would still begin on carbon number 2. So this is going to have a very similar name to the last compound, except since the alkene begins on carbon number 2, we name it 2-butene. We use a very similar process for the alkyne here. The only difference is, since this is an alkyne, instead of its ending being ane or ene, its ending will be ine. So this will be 1-butyne. And similarly, this compound will be 2-butyne. Let's practice some with skeletal structures. So let's take a look at this molecule here. We first want to find the longest chain that contains the double bond. So there's only one chain here, and it's clearly got 5 carbons. which way do I want to number? Well, if I number starting on this side, 1, 2, the alkene begins on carbon number 2. And if I number from this side, 1, 2, 3, it begins on 3. So 2 is better. We want the lower number, 2. So 5 carbons would be pentane. Because it's an alkene, it becomes pentene. And since it begins on carbon number 2, this is 2-pentene. This molecule to the right is very similar in structure, except that it has 1 additional carbon. Which way are we going to number? Well, if we number from the left, 1, 2, 3, 4, it's not until carbon number 4 that we get to the alkene. So we want to number from the right in this case, because that will get us to the alkene on carbon number 2. So this has 6 carbons, so the parent is hexane. Because it's an alkene, we change the ending from hexane to hexene. And then we say that the alkene begins on carbon number 2. So this is 2-hexene. Skeletal structures can sometimes be confusing when we're talking about alkynes, and I generally try to refrain from using them with alkynes, but it doesn't hurt to take a look at a simple example right here. So how many carbons do we have? This is where people make mistakes. So this is the N, that's a carbon. This is a carbon. That's considered a intersection right there. So 2, here's a carbon, 3, 4, 5, 6. So the parent name is hexane. We want a number from the left so that the alkyne begins on carbon number 2. So this is going to be 2-hexyne. Yne indicating that we have an alkyne. And finally, we have a molecule that is perhaps a little bit more challenging. We need to find the longest chain that contains these 2 carbons. So for example, I couldn't go 1, 2, 3, 4 because that is missing this carbon right here. So let's go ahead and mark that chain. So the longest chain that contains those 2 carbons right there, I think, is pretty clearly here. Uh-oh, and do I go down or to the right? Doesn't matter because it's essentially a methyl group either way. You'll get the same name. Okay, so the longest carbon chain is 1, 2, 3, 4, 5, 6. It's a hexane parent. Because it's an alkene, it's going to be something hexene. How do we number? Now here we have to be very careful. Initially, it has nothing to do with these carbons here, the substituents. We have to give the alkene the lowest possible number. So if we number from the left, 1, 2, 3. Okay. And if we number from the right, 1, 2, 3. Well, that doesn't help. It's going to be 3-hexene no matter which way we go. So what we do now is we turn to substituents as the tiebreaker. So we follow the old rules at this point and say we want the first substituent to have the lowest possible number. So we haven't completely rejected the old rules, we just had to modify them a bit. Alright, so if we number from this side, 1, 2 is where we get that first functional group. And if we number from this side, 1, 2, 3, that's where it is. Okay, so we're going to number from the right so we get to this carbon in as low a number as possible. So this is a CH3, correct? And this is a CH3. Those are called methyl groups. So substituents get listed first in the name, and they are on carbon 2 and carbon 4. So this is going to be 2,4. Since there's 2 of them, we say dimethyl 3-hexene. So again, 2, 4. Remember, we separate numbers with commas. Dash dimethyl, because there's two methyl groups here, dash 3 dash hexene. And remember, we always separate numbers from letters with dashes or hyphens. Here I have two molecules which seem to have a very similar structure. The only difference is the structure on the right is an alkene. It has a double bond. The structure on the left is an alkane. There is no double bond. But we're going to see that the naming is fairly different in one respect that's important. So what's the longest chain? Be very careful. Don't just go 1, 2, 3, 4, 5, 6 left to right. No, the longest chain includes these two carbons. So 1, 2, 3, 4, 5, 6, 7. So the parent is heptane for 7 carbons. This right here is a substituent. So let's mark that off. So that is the longest chain right there. Okay, and that is a substituent. What do we call those? We call those, again, methyl groups. So this will be 1, 2, 3, 3-methyl heptane. What about this structure? Again, we need to find the longest chain, but it's not the same longest chain because the rules, recall, say that you have to number through the chain. You cannot leave off that carbon at the end. So these carbons have to both be in the longest chain. So if I go up, the longest chain would be only 4 carbons. If I go this way, the longest chain is 6 carbons. So 6 carbons would be hexane. Since it's an alkene, we change it to hexene. We're going to number so that this gets the lowest possible number. So carbon number 1. So it's 1 hexene. But we have to name the substituent here. And the substituent is 2 carbons. That's called an ethyl group. So it's going to be 2 ethyl, 1 hexene. The rules for naming the cycloalkenes are not substantially different from the rules for naming cycloalkanes or alkenes. They're kind of a combination of all of those. So let's take a look at some examples, and this will allow me to call out the most important points. So recall that if there's only one substituent, the rule was that that substituent is automatically carbon number 1. Again, functional groups are considered more important than substituents. So we modify the rule slightly and say that the functional group automatically gets carbon number 1. Now that makes a bit of a problem here because there's 2 carbons, correct? So one of these has to be number 1 and the other one has to be number 2. We have to number through them. So which way do you think we're going to do it? Well, if we make this one number 1 and this one number 2, then the methyl is on 2. If we make this one number 1, the methyl is on 1. So again, the rule is you want to give the functional group the lowest number, and then once you've done that, you then consider substituents. So this will be carbon number 1. There's a methyl group on carbon number 1. So this will be 1-methyl, cyclo, because it's a ring, and this would be pentane, but there's a double bond here, so it becomes cyclopentene. So the name is 1-methyl cyclopentene. Look at the compound to the right. This compound is clearly an isomer. They both have the same molecular formula, just different connections of atoms. Okay, so this is also going to be something methyl cyclopentene. What we have to do is figure out how we're going to number. Well, again, one of these has to be carbon number 1, and the other one has to be carbon number 2. You have to number through it. So if this is number 1, then this would be number 2, and this carbon would be 3, 4, 5 methyl. On the other hand, if we make this carbon number 1, this would be 1, 2, 3. And we want the lower number. So this will be 3-methyl cyclopentene. The last one is a bit trickier. Again, remember that we have to number through the functional group here, and one of these has to be automatically considered number 1. So let's say this is number 1. If this is number 1, then this has to be number 2. So let's make this carbon number 1. This is number 2. The first substituent we get to is on carbon number 3. Okay. What happens if we go the other way? 1, 2, 3. Same thing. All right, we need to continue the game to see if we get a tiebreaker. 1, 2, 3, 4, 5, 6. Okay, so it would be 3, 6 going this way. If we go the other way, 1, 2, 3, 4, 5, 6. It's 3, 6 either way, so it doesn't matter. The naming is going to be the same. So there's 2 methyl groups here. So this is going to be 3, 6 dimethyl. And this now has 6 carbons, so cyclohexene. 3, 6 dimethyl cyclohexene. Let's go ahead and take a break here, and I'll be posting the next video right after this.